Hello, good people. Welcome to video number one of a range of topics here in Unit 8. So, Unit 8.4 or Unit 8, Section 4, 5, and 6 all have to do with finding areas between curves. So, we know that the definite integral from a to b of a specific function represents, and I'll draw an arrow here, represents the area that's trapped between the x-axis and a specific function, right? We know that this area is represented by the integral. And what happens when the shaded area or the area that I'm looking for is not right up against the x-axis? What if it's something like this? And it's actually trapped between two curves. And so topics 8.4, 8.5, and 8.6 handle that situation of areas that are between two curves. We're going to find the areas by taking, I guess you could call them Riemann rectangles vertically or horizontally, or we might have a mixture of both. And that's really what 8.4, 5, and 6 are all about. So let's start by taking a look at this situation. We have two functions. And the area that's bounded by those two functions, the area that's trapped, is the area that we're looking for. Now, obviously, you can take a look at the shaded area. This is not a geometric shape. This is not a circle, a rectangle, trapezoid, triangle, whatever. It's not a normal shape. However, I do know how to find the area between two curves because what we're going to need is two pieces of information. We need to know where the functions intersect. Now, why do I need to know that? Where the functions intersect? Well, because I need to know a starting point and an ending point, right? I need to have my a to b. If I'm going to build an integral, I need to know where to start and where to end. So I need to know those intersection points. And then the second thing we need is we need we need to know which function is on top, and I'm going to put on top in quotation marks, and which is on bottom. Another way to say that is I need to know which function has the higher value, because when you think about what we're going to do, we're going to need to establish the upper bound function and the lower bound function to determine the height of my rectangle. So this is what we're going to do. We're going to build rectangles that are really, 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 really thin strips like this, right? And so we're building these rectangles as best as we can here. So very much like a Riemann sum allowed us to build rectangles and then add those rectangles together, right? Now, if I make the widths of my rectangles smaller and smaller and smaller, that means I'm going to be able to add more and more rectangles. And this area here, that error, is going to go away. And we'll get the exact area under the curve. That's what the definite integral did for us, right? The definite integral said we take rectangles, but we take the number of rectangles and we're going to increase it to infinity. Well, if we have an infinite number of rectangles, these slices become really, really thin, and we are going to get a very, 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 very compacting of the rectangles to where it actually equals, if we take an infinite number of rectangles, it actually equals the area that's trapped. Okay, so here, when you think about it, the height of the rectangle, which is this, is going to be whatever the top function is minus the bottom function. Now, why does this work? Well, if we know what the top function is, and I'm going to do that in green, if we know what the top function is, that means if we were looking, let's say we were looking at something like this on a grid, right, on a coordinate plane. If we were looking at this top function would represent the y value here, and then the bottom function would represent the y value over here. And if I subtract the top minus the bottom, well, that's going to give me this distance, which we know as the height. So in order to find the area of just one of these rectangles, we're going to find the height times the width. Now the width is going to be my delta x, the change in x, which is really, really, really thin, right? It's infinite. It's going to become infinitesimally small. And so we're going to multiply h, which is the height, times the width, which is this base, right? The delta x. But the height is going to depend on which is the top function, because that's going to give me the top y value, which is the bottom function, that's going to be the bottom y value. And if I subtract those, I'm going to get the distance in between them, which is the height. So top minus bottom, whenever we're creating our rectangles vertically, perpendicular to the x-axis, right? They're making 90 degrees with the x-axis. Then that's going to be my setup. So when I come over here, here's what we can say. One rectangle is equal to base times height. As a matter of fact, you know what? I'm going to switch it around. I'm going to say height times base. And here's why. The height is going to be the top function minus the bottom function. And the base is going to be my delta x, the little skinny width of that strip rectangle that we just created up here. That's how I'm going to do the area of one rectangle. But we want to add an infinite number of rectangles. So we're going to take an integral from the start to the end of this setup. And so we're going to look at number one, and we're going to try to see if we can figure number one out. So the first thing is, do I know what two functions we're talking about? Yes, we're talking about the area bounded between the curve x squared plus 2x plus 1 and the line 2x plus 5. So you should be able to know which equation is which graph. So I'm going to go ahead and highlight that this is g of x, that's the line, and this is the curve f of x. Okay. Now, do I know where they intersect? Oh no. I sure do know where they intersect. I can see that they intersect at x equals negative 2 and x equals positive 2. So we're looking for the shaded area between them. It's almost a Nike logo here, but not really. Don't sue me, Nike. So this is the area we're looking for. All right, so we're going to take an integral from negative 2 to 2. But let's check. In that window, in that interval between negative 2 and 2, is one function always the top and the other function always the bottom? So if I were to draw a representative rectangle, and I'm just going to pick a random place and draw a rectangle here, is the top part bounded by the same function forever in here? So if I do another rectangle in another random place, is the top part always the same function? Yes, it's always g of x. And is the bottom function always the same boundary function? Yes, it's f of x. So therefore, we're going to take the integral from negative 2 to 2 of the top function, which is g of x, minus the bottom function, which is f of x, because that's how we're going to find one little strip by doing this. And then my delta x becomes my dx. So this part right here is right here, because that would have given us one rectangle. But we want to add an infinite number of rectangles, which is why we're doing the integral from negative 2 to 2. An integral is an accumulator. It's accumulating all these areas of rectangles. And my area of rectangle is given by g of x minus f of x times dx, which stands for my delta x. So if I can figure this out, I'm done. Great. Can I figure this out? I don't know. This is equal to, oh, I keep losing my page. I apologize. This is equal to the integral from negative 2 to 2 of the top function, minus the bottom function. Why am I using parentheses? Because when I'm subtracting the second one, I got to make sure that I keep track of all the minus signs here. If you simplify this, I believe you're going to get negative x squared, because that's subtracting, minus 2x, and the plus 2x are going to cancel out. Minus 1 and plus 5 is going to give you plus 4. So really, we're just taking the integral from negative 2 to 2 of that resultant dx, right? So minus, minus, minus. Everybody got the minus. And then 5 minus 1 was 4. 2x minus 2x was 0, and then I'm just left with minus x squared. So this is what I'm left with. Great. Can I solve this by just taking the antiderivative? Add 1 to the exponent divided by the new exponent. This is 4x, and we're going to evaluate that from negative 2 to 2. So substitute the 2 in there. Make sure to cube it, don't square it. Plus 4 times 2. This is going to give me the first part, minus, plug in the bottom limit into there. Cubed divided by 3 plus 4 times negative 2. All right. And then this is, let's see, negative 8 thirds plus 8. Here I have to be careful. Minus a minus, so that becomes positive. But then this becomes negative 8 over 3. So it does become a negative. Or you can think of it as negative 2 to the third power is negative 8. And then the opposite of that would be positive 8. Oh, but I'm subtracting, so minus 8 thirds. And then this would be plus, be very careful, because it's subtracting a negative 8, so this would be plus 8. So my final result would be 16 minus 16 thirds, or 32 thirds, and this is the exact area that's in between those two curves. How did we figure it out? We figured it out by taking an integral of the top function minus the bottom function. So if I'm finding strips, a little rectangle, and we're adding up all those little strips to accumulate all of this area, then that's the setup that I would need. We're going to come back in the next video, do some more examples, and kind of get the hang of it. But the main idea is, if we're looking for the area between two curves, which function is the top function, which function is the bottom function, and then just do top minus bottom of the integral between the start of the shading to the end of the shading. And that's it.